Good morning, everyone. I'm Furukawa from Simon Fraser University. I'd like to first thank the organizers for inviting me for giving a talk. It's really great an honor to be speaking with so many other great people in the list. I often say this when giving a workshop talk, but I really feel that the workshop tutorial are the most exciting piece beyond the main conference itself because I can really deliver my own free will. I somehow feel that the paper, when writing a paper, I don't have the freedom of speech because I feel that I'm scared of reviewers and can't really write what I believe the most important. And today, this is the message I want to deliver. CVPR is a contemporary art exhibition. Given that we have so many other great people giving great technical content, I thought that I can give a bit unusual talk, although I tend to make my talk always unusual. And hopefully you get what this means at the end of my talk today. And also I want to mention that I realized that I said yes to giving a talk at the another scene understanding workshop, this one indoor scene specifically. I'm trying to deliver the same message with more technical content. So if you like my talk, please go to the other workshop, which is also pretty exciting. I have been working on reconstructing or modeling or CAD level geometry. It's a bit difficult to define, but look at the video. This is a making video for the movie Transformer. The bottom is a final clip. To really make that happen, people, professional designers, modelers, make these models in CAD quality, or in other words, structured geometry or semantically segmented geometry. The last one is my own invention, terminology. So the geometry has segmentations with respect to underlying geometry, semantics. And these models are very effective for, say, human model editing or effect mapping, physics simulations, making interactions easy, making analysis easy. So many benefits immediately available for applications. Not at that level of quality, but our group has been working on making that kind of models from outdoor, indoor, ground level sensor data, remote sensing from the air, etc. So let's look at these set of papers from our group on structured geometry reconstruction. And I think these papers are all great success. The papers got accepted to top tier vision conference. And often students have these papers on resume. They get great offers from great companies and good life. So it's a great success. But I want to set a standard high for myself. I want to rank these papers, rate these papers based on the impact to the real world or the impact to the people outside computer vision. Do they find my work exciting or useful? And here is my rating. At the left, no impact, right? Impact. So green smiley icon here, meaning was actually used for real production, so real impact. The left is the angry face icon. So this is the angry face of engineer who implemented it, tried it, found out that it doesn't work at all. So it's showing the anger of engineer. And if you are a first year student, graduate student, you may be shocked. Oh, research mostly useless. It's shocking. Or if you're already experienced in the field, you may be surprised to see. Oh, you have nearly a quarter of your research making an impact to the real world applications immediately. So both are actually, I think, good views. But my message is not really actually bad. So to begin that message, let me introduce an essay written by Aaron Hertzman, posted a few weeks back. He always writes amazing essays and articles. I highly suggest you to read it. This is about the contemporary art, with some reference to the computer graphics or computer vision community. What I want to mention is a comment posted by Alyosha Efros. You can read here, but this portion, 90% of CVPL papers will turn out to be a junk, either immediately or after a few years. So is 90% of contemporary art. So this is not the main message by the Aaron's essay, but you can also interpret that most of the contemporary art is actually a junk, which community doesn't bother eventually. So I'm adding these three words, but in short, CVPL is a contemporary art exhibition. Most are junk. And if you can find a few pieces that really speak to you, it's a great success. And I also agree. My experience tends to be like this. I'm really looking for a few shining pieces which talk to me. And Aaron replied with some Wikipedia article, Sturgeon's Law. It says something like that. In many fields, 90% of things, everything is crap. Now, getting back to this, you may think, really, most of my stuff actually are not interesting to people outside computer vision. So, from the perspective of computer vision people, all these may be a success, but for the majority of the others in the world, people outside computer vision, my work is actually useless. Uh, Maybe disappointing, but my message is not really. It's not really that bad because there are many shining ideas here. The paper itself, the system itself may not be really ready for the production, the real use, but there are shining ideas which actually propagate through other work and eventually lead to impact. For example, these two ideas, the paper themselves are not ready, but lead to the work with impact, which really used for real production. And there are ideas which I believe is really shining piece. So this paper, ICCV 2015, I think amazing idea, but was not really used for production yet. But I feel still has a potential. We just didn't meet such on a paper work yet. Has a potential. Or there's idea which actually started out here a long time ago, lead to another work, best student paper award, but actually no outgoing edge. So I kind of gave up on the idea, unfortunately. So this maybe idea could be actually a junk in that definition, didn't end up leading to the impact. However, this paper, the original idea, was from Manhattan World Studio paper. Fairly decent citations, nearly 400. So this idea should not be a bad thing, given that we really care about citations. And in fact, indeed, this idea was not a junk or garbage, because maybe a junk, but it actually has impact eventually, because I'm not drawing the negative influences. So these red arrows are the negative influences. It's more like we did this, and we found that it was actually a bad idea. So the bad idea helped me go to the right direction, lead me to the right direction. So these are the red arrows. So this idea actually eventually led to impact. So actually in this diagram, many of my ideas lead to impact. So this idea led to impact. This idea, unfortunately, not yet. And this idea, unfortunately, not yet. But if this one actually makes it through, this idea actually leads to impact. So actually not bad. So also, idea from other researchers. Actually, this arrow is coming from the other subfield, recognition. So I borrowed the idea from recognition and used in reconstruction. Or sometimes the idea apparently doesn't have the source. It's nothing close to anything I've seen so far. So my student Chen Liu suddenly came up with the idea out of apparently nowhere, or maybe he has his own incoming arrows, but I didn't see, in my view. And that idea may contribute to real impact. So this is really maybe the most important slide, my research idea flow. Out of all the papers and research activities I'm doing with my students and postdocs, this is how my ideas really flow and seeking to push to impact. Now I want to take piece by piece and explain with a little bit more content what the message, lessons I learned, this part of the diagram. The first piece is left around here. So when I do research around here, I was more and more confident this is the message, which is top-down procedure is better than bottom-up, and you want to detect higher level primitives. This is what I mean. Let's think about a floor plan reconstruction task. You go to a house with a 3D tracking phone like Google Project Tango or a Matterport-style 3D scanner. You get 30 points. You scan, then seeking to recover a floor plan like this as a vector graphics image graph structure. If you're asked to do this task, most people do the following in a bottom-up procedure. You first do corner detection. These days, you annotate train convolution neural network, any standard combinate, you can do corner detection. But the problem is you may miss one or two real corners, like here at the bottom left corner, top left corner. And once you miss this corner, the next procedure step is to find connections between detected corners. Usually enumerate many possible line segment or edge candidates, then choose the correct subset. And if you miss one corner in enumerating corner candidate, you automatically miss enumerating correct edges, and you miss generating the proper room. So one mistake in detecting correct corner, it's going to be a mistake for sure. So most papers actually are bottom-up in the past and follow this dilemma, pitfalls. You can't miss a single true primitive, so you have to enumerate much more than necessary, and the number of primitives to generate grow exponentially because the primitive degrees of freedom grow. So corner, you have 2 degrees of freedom, not bad. Edge, 4 degrees of freedom. You have to enumerate room candidates, it's a lot. A room may have 4 corners, 6 corners. The number of parameters grow, and the space of the potential shape of a room grow exponentially. So really, this procedure falls apart. So the message is the top-down is better. So here, top-down meaning you want to detect a region, 2-dimensional primitive, instead of 1-dimensional primitive edge or 0-dimensional primitive corner. You want to detect 2-dimensional higher level primitive, which is a region. Because say to detect a room here, you actually don't have to worry about detecting corner here or here. Because of occlusions or clutter, 3D sensor may not capture corner clearly well, but actually doesn't matter because looking at these information all together, you're confident that there gotta be a room here, region. So room detection is much more robust than room corner detection. Intuitively, that makes sense, hopefully. So you want to detect region first. And once you get these 7 regions detected, 6 regions, then you do some procedure, top-down procedure to find now edges or corners. This procedure is actually not easy, but there are ways. And if you manage to do this, getting 0-dimensional corners, 1-dimensional edges from 2-dimensional regions, that procedure is going to be a lot more robust than a bottom-up. So that's the lesson I learned around here, and which really the idea propagate through to many of our projects. So now, the idea, the failure here lead me to do top-down in this research, ECCV 2018. So in the top-down procedure, we want to use a shape grammar as a domain knowledge. But turns out that's a bad idea because it is a restrictive shape layer, not really general enough to handle real examples. Unfortunately, this idea does not have any outgoing orange arrow, meaning the idea I personally see is a dead end. It's a bad idea, actually. You shouldn't actually do this. Although that doesn't lead me to the other direction. So still lead to impact potentially, but the idea itself was a bad one. So what that means, at the top you see a shape grammar. So this is a set of rules defining how residential house is built. So the first rule here, starting from empty land, you choose the type of a foundation. Say a foundation consisting of a one rectangle, two rectangle, three or L-shape, U-shape. Given the foundation, for each foundation you can specify the roof type, say a gable or a hip roof. And after that you can add the dormers, chimney, garage, etc. Given a raw sensor data, say LiDAR, a point cloud, LiDAR mesh, you essentially solve for the classification problem. Which rule branch you should take? Say two rectangle branch or U branch. You solve a sequence of classification and also regression tasks to estimate geometric parameters associated with each rule branch. So you solve for the sequence of classification and regression tasks to reconstruct this kind of a building. You can actually get pretty cool building models which look like a CAD quality and make a nice pretty video. But the issue is these actually look nice, but the kind of the buildings, houses which we can reconstruct are fairly limited. We in fact ignored nearly 40% of the examples we collected because our grammar cannot represent. And even before that, we avoided getting data from London, center of London, because those buildings are too complicated. So we only collected data from the suburbs of major cities in UK. And even after that, we ignored 40% of the buildings because too complicated. So left, we can maybe still handle, but as you go to the right and right, more and more complex. So real buildings, grammar just cannot model. It's difficult to even change grammar manually to make it work. So the top was the idea of the workflow we had when writing the paper. So we want to build a shape grammar as a domain knowledge representation. We did it manually for the paper, but there is a field called inverse procedure modeling, which takes many examples, turn into a shape grammar. Unfortunately, inverse procedure modeling is struggling. There's not good system for a complex structure, in my view. So we use manual design, and so this procedure is actually a bad idea because you cannot really represent explicitly grammar, which can cover a wide range of buildings in the real world. So this led me to the other idea, the opposite direction. Maybe this is a good idea. Actually, we are not sure yet because we haven't reached the impact yet. But the idea was maybe taking these examples, instead of solving through procedure, inverse procedure modeling, procedure reconstruction, 2 steps in one shot, using some big data machine learning techniques, which may mean deep learning by now, somehow go straight. So implicitly extracting shape grammar rules, then use for reconstruction tasks. That's what we are still exploring. But this is the example how the idea here turns into negatively towards my current research projects. And so this leads to another paper, this year CVPR. We have another idea flowing from this side. So let me talk about this first. This is an example where idea really came out of nowhere from my student, Chen Liu. The idea was deep learning really enables the use of powerful optimization method instead of replacing existing optimization techniques. And this is what I mean. So this time, maybe think about the outdoor architecture vectorization. Take, say, Google Maps satellite image, trying to parse architectural structure like a graph, a planar graph. So you may do using a detector, corner detector, edge detector, or region detector. Use some optimization, so integer programming, and you get the model. That's what we did. And the discovery, although many people don't look at the paper like this, was before deep learning, we often use graphical model inference, or maybe this is the only way to solve computer vision problem in the past. Graphical model inference for in the case of labeling pixel, we use MLF, which is amazing actually machinery. There are many great papers in developing good MLF methods. You can handle a few million variables, really scalable, but the inference power was weak. Only usually potential pairwise potentials, mostly submodular potentials. On the other hand, IP, it's very powerful. Higher order potentials, non-submodular. You can handle many complex potentials or energy functions, but it's not scalable. A few hundred variables at most. If you go beyond, it is exponentially worse because likely your problem is NP hard. But what we found was really deep neural network shrinks the candidate pool to a small set or derives good potential, which makes your energy slope nearly convex or easy to optimize. So DNN really allows us to use IP, very powerful optimization machinery, to infer the last bit of the problem, complex graphical topological inference, which DNN cannot really do, but IP can do. So this was the message. Here's another example here. This is the example where we use the technique from recognition community, instant segmentation, like mask our CNN from Facebook. We realized very early on, maybe 2017, we actually realized this. The segmentation techniques actually works for geometric segments. So originally, instant segmentation works for semantic rich classes. So finding a human against cow, or grass, a house, or bicycle, where each instance has a clear the meaning category. But it turns out that the same machinery works well for semantic weak instances. Say, given an indoor scene, you have many wall segments. Every segment is the same wall. You can actually find the instances pretty well by the same machinery just by changing the annotations. So this is an idea we really borrowed from the other sub-community. And last example here, so our paper. This really uses two lessons in a negative way, in the opposite adversarial way. So first of all, actual optimization was a great idea, it really made impact, but too complicated. Engineer is going to be angry because very complicated. It's difficult to really do right. So we have some neural ways of doing topological inference without using complex optimization. And also explicit grammar, shape grammar was bad. So we are really trying to exploit some implicit grammar, shape grammar learning. This happened. Although this impactness goes down worse, but hopefully leads to something good in the future. So this is really my research idea flow. And what I ultimately hope is my research are going to influence others, not my group, my people, other people in a positive way. Or may it be really bad if it influences negatively. People look at my papers and found out these are bad ideas. Don't do this. This is also a great contribution. As long as people look at my paper, no arrows are bad, but some arrows, even negative ones, are good, I think. So here are my messages. CVPR is a contemporary art exhibition. Many ideas may be garbage, but actually in my case, garbage ideas lead to impact. CVPR is starting now. Please enjoy. Hope you find a few of your masterpieces that talk to you. Thank you.